Let's start. We'll start by recalling what we saw in this week. So, the first thing that you saw this week was that the problem of computing the permanent of a matrix with 0, 1 entries is sharply complete. Recall that for an n cross n matrix A, its permanent is the following polynomial. Permanent of A is equal to sum over sigma in Sn, where Sn is the set of all permutations on the set 1 to n. Product I in n, A I sigma I. Then you saw Toda's theorem. This theorem states that the class PH is contained in Fp to the sharp P. Then in the proof of Toda's theorem, you saw a class parity P, and a language L is said to be in the class parity P if and only if there is a polynomial time non-deterministic Turing machine N such that X is in the language if and only if the number of accepting parts of N on input X is odd. This should be N. There's a typo here. I'll correct it. And then you saw the language parity set. And parity set is the set of all Boolean formulas phi with an odd number of satisfying assignments. So now let's move on to the problems. The first problem that we'll see today is the following. Which of the following problems are in the class Sharpie? Select all that are correct. The options are the problem of deciding if a given Boolean formula is satisfiable, the problem of counting the number of satisfying assignments of a given Boolean formula, the problem of counting the number of falsifying assignments of a given Boolean formula. So an assignment is said to be falsifying if that makes the formula evaluate to false. Option D is the problem of deciding if a given graph is three-colorable. And option E is the problem of counting the number of proper three colorings of a given graph. So the answer to this question is options B, C, and E. Let's see why. So first let's rule out options A and D. So option A and D are both decision problems, and Sharpie is a class of counting problems. So A and D cannot be in P, Sharpie. Now option B is exactly the Sharpset function. And now recall that Sharpset function is the function of the so is the function that counts the number of satisfying assignments for Boolean formula. Now there exists a non-deterministic Turing machine N that does the following. Given a Boolean formula phi in n variables x1 to xn, it guesses an assignment a1 to an and then deterministically checks if phi a1 to an equals to 1 or not. If phi of a1 to n equals to 1, the machine outputs 1, and if phi of a1 to n is 0, then the machine outputs 0. Now clearly n is a polynomial time non-deterministic Turing machine, and every part in the computation graph of n on input phi corresponds to an assignment. This is because the only non-determinism that n uses is to pick or guess the assignment a1 to an. Everything that it does after that is done deterministically. So every path in a computation graph of n on input phi corresponds to an assignment. And also the number of accepting paths is exactly equal to the number of satisfying assignments, because for an assignment a1 to an, n accepts if and only if phi evaluated at a1 to an is true. So this statement is clearly true. And so B is in Sharpie. Why? Because in Sharpie, so a counting problem is in Sharpie. If so, a function f is in Sharpie if f of x is equal to the number of accepting paths of a certain polynomial time non-deterministic Turing machine on input x. So B is clearly in Sharpie. Now let's look at C. For C, consider a non-deterministic Turing machine n prime that does the following. Given a Boolean formula phi in n variables x1 to xn, it guesses an assignment a1 to an and then deterministically checks if phi of a1 to n is 1 or not. If phi of a1 to n is 1, it outputs 0, and if phi of a1 to n is 0, it outputs 1. So basically if n prime outputs 0, if and only if n outputs 1 and vice versa. So clearly n prime is a polynomial time non-deterministic Turing machine, and just like n, every path in the computation graph of n prime on input phi corresponds to an assignment. However, in this case, the number of accepting paths is exactly equal to the number of falsifying assignments of phi, because n prime accepts if and only if phi of a1 to an is 0, that is if a1 to n is a falsifying assignment of phi. So C is also a sharp P. Now let's look at option E. So option E is the sharp 3 color function. So we call it a sharp 3 color function counts the number of valid 3 colorings in a given graph. Now there exists a non-deterministic Turing machine n double prime that does the following. Given a graph G with n vertices, it guesses a coloring C1 to Cn in 0, 2 to the n. So a 3 coloring can be naturally expressed as a string is 0, 2 to the n. So let's say if I want to color vertex 1 with color 1, with the first color I would give it colors, I would give it 0. If I want to color vertex 2 with the third color, I would give it color 2 and so on. So it guesses the coloring C1 to Cn in 0, 2 to the n and then deterministically checks if this coloring is a valid 3 coloring or not. If it is, n double prime outputs 1, otherwise it outputs 0. Now clearly n double prime is a polynomial time non-deterministic Turing machine, and furthermore every path in the computation graph of n double prime on input G corresponds to a 3 coloring, corresponds to a valid 3 coloring. Sorry, corresponds to a 3 coloring, right? Also, the number of accepting paths is exactly equal to the number of valid 3 colorings. Why? Because n double prime accepts on a coloring if and only if that coloring is valid 3 coloring. So the number of accepting paths is exactly equal to the number of valid 3 colorings, and so E is also in sharp P. So options B, C, and E are in sharp P, but A and D are not. Now let's move on to the second problem. If NP is not equals to co-NP, then which of the following options can be inferred? Select all the options that apply. The options are P not equals to NP, FP equals to sharp P, FP not equals to sharp P, and P not equals to co-NP. The answer to this problem is option A, P not equals NP, option B, FP not equals sharp P, and option D, P not equals to co-NP. Let's see why. So we have seen this multiple times in the past sessions that a language L is in P if and only if its complement is in P. So if P equals to NP, then NP equals to P equals to co-NP, and we get a contradiction. Similarly, P equals to NP gives a contradiction. So what do we have? We have that NP equals to P and P equals to co-NP are both contradictions. So NP not equals to P and P not equals to co-NP are true. So we get options A and options B. Now let's look at options B and options C. Now, if option B is true and if FP equals sharp P, then P equals NP. Why? Because, well, for any problem in NP, if FP equals to sharp P, you can count the number of accepting paths in the corresponding non-deterministic Turing machine. And if the number of accepting paths is at least 1, you know that that string is in the language. If the number of accepting paths is less than 1, that is it's 0, then you know that the string is not in language. So this gives you a polynomial time algorithm to decide any language in NP. So FP equals to sharp P implies that P equals NP. And as we saw above, P equals NP leads to a contradiction. Therefore, FP equals to sharp P leads to a contradiction. So FP equals to sharp P has to be false, but its negation, FP not equals to sharp P has to be true. So the answers are P not equals NP, FP not equals sharp P, and P not equals co-NP. Now let's move on to the third problem. So the third problem asks, Which of the below statements would imply that P equals NP? Select all that apply. The options are: there exists a deterministic polynomial time algorithm to count the number of falsifying assignments for Boolean formula. There is a deterministic polynomial time algorithm to count the number of proper three colorings of a graph. There is a deterministic polynomial time algorithm to count the number of spanning trees of a graph. And there is a deterministic polynomial time algorithm to count the number of directed ST paths where S and T are specified vertices in a directed acyclic graph G. So the answer to this problem is options A and B. There is a deterministic polynomial time algorithm to count the number of satisfying assignments of Boolean formula, and there exists a deterministic polynomial time algorithm to count the number of proper three colorings of a graph. Let's see why. So if A and B are true, then SharpSat and sharp three colorable would be in FP respectively. Now both SharpSat and sharp three colorable are Sharpie complete. So if these are in FP, this implies that FP equals Sharpie, which, as we saw in the previous question, implies that P not P equals NP. So if A and B are true, we can conclude that P equals NP. What about C and D? Now, we know that sharp spanning trees is in FP. This we saw in the class. Also, the number of ST paths in a directed acyclic graph can be computed in polynomial time by a simple dynamic programming algorithm. So this is a very simple dynamic programming algorithm. Try to find it on your own. If you can't, you can either post a question in the forum or you can ask me in the next session. Yeah, so the number of ST paths can be computed in polynomial time using a dynamic programming algorithm. So C and D are in FP and they do not imply P equals NP. Now let's move on to the next problem. The next problem asks, as per the current understanding, if sharp spanning trees is sharp spanning tree an example of a Sharpie complete problem or not? The answer to this question is no, and the reason is the following. As per our current knowledge, sharp spanning trees is in FP. This we saw in the class. So if sharp spanning trees were Sharpie complete, then FP would be equals to Sharpie, and therefore, as we saw in the second problem, P would be equals to NP. But however, right now, P versus NP is an open problem. So according to our current knowledge, sharp spanning trees is not an example of a Sharpie complete problem. So the fifth problem is, which of the following problems are known to be Sharpie hard? Select all that is or are correct. The options are permanent of an n cross n matrix with entries from 0, 1, permanent of an n cross n matrix with entries from -1, 0, 1, permanent of an n cross n matrix with entries from 0 to m for a positive integer m strictly greater than 1, and permanent of an n cross n matrix whose all entries are equal to m for a positive integer m greater than or equals to 1. The answer to this problem is options A, B, and C. Let's see why. So every matrix with entries in 0, 1 is also a matrix with entries in -1, 0, 1 and 0 to n. Thus, we can compute the permanent of a matrix with 0, 1 entries given Oracle access to algorithms that can compute permanent of matrices with entries in -1, 0, 1 and 0 to n. Now, as the problem of computing the permanent of a matrix with entries in 0, 1 in Sharpie complete, so is the problem of computing the permanent of matrices with entries in -1, 0, 1 and 0 to n. So both the options B and C are Sharpie hard because the problem of computing 0, 1 permanent reduces to these problems. Cook reduces to these problems in polynomial time, or Turing reduces to these problems in polynomial time. So these two problems are Sharpie hard. So that settles A, B, and C. A is directly known to be a Sharpie hard. So that settles A, B, and C. Now let's look at D. Now, if A is a matrix so that all of its entries are M, then permanence of A is, by definition, sum over sigma in Sn, product over I in N, Ai sigma I, is equal to sum over sigma in Sn, product I in N, M. Now, we can take this product I in N, M common. This is exactly M to the N. So once we take this out common, we are left with sum over sigma in Sn times, so sum over sigma in Sn1, that is n factorial because there are n factorial permutations. So this expression is exactly equals to m to the n times n factorial. And it's not too difficult to show that m to the n times n factorial can be computed in time, which is polynomial in n and log m, which is exactly equal to the size of the input. So since A is an n cross n matrix and all of its entries are n, the input size would be n square times order log n. So order log n, order n square times log n. And you can compute this quantity in exactly that much time. It's not too difficult to show. You can try it on your own. And if you still can't show it, you can ask me in the next session. So option D is in FP. And since we don't know if FP equals to Sharpie or not, it is not known to be Sharpie hard. So that's problem 5. Then let's move on to the next problem. Suppose phi is a Boolean formula on n variables x1 to xn. Let phi prime equals to phi and x1. Let sharp phi and sharp phi prime denote the number of satisfying assignments of phi and phi prime respectively. Then which of the following options can be inferred? Sharp phi equals to sharp phi prime. Sharp phi is less than or equals to sharp phi prime. Sharp phi is greater than or equals to sharp phi prime. And option D, sharp phi plus sharp phi prime equals to 2 to the n. The answer to this problem is that sharp phi is greater than or equals to sharp phi prime. Let's see why. So this is what phi prime is. Phi prime is phi and x1. So phi prime is true if and only if phi is true and x1 is true. So every satisfying assignment phi prime is also a satisfying assignment of phi. Why? Because if a1 to an satisfies phi prime, then phi prime a1 to an is true, and therefore phi a1 to n has to be true. So this directly shows us that the number of satisfying assignments of phi is greater than or equals to number of satisfying assignments of phi prime. So option C is correct. Now let us see why options A, B, and D are wrong. So option B is false. Okay, so let phi be x1. Then what is phi prime? It's x1 and x1 complement. Now the number of satisfying assignments of phi is 1, but the number of satisfying assignments of phi prime is 0 because x and x1 complement is a contradiction. So number of satisfying assignments of phi is strictly greater than the number of satisfying assignments of phi prime. Now, what does option B say? It says that the number of satisfying assignments of phi is less than or equals to number of satisfying assignments of phi prime. But we have constructed a formula for which this is not true. So option B is false. Option A is also false because option A says that sharp phi is sharp phi prime, but this formula that we have constructed, for this formula that we have constructed, sharp phi is strictly greater than sharp phi. So let me write it like this. The first option B works. So option A is also false. Now let's look at option B. So let phi equals to x1 and x2 and x3. Then phi prime is x1 and x2 and x3 and x1 complement. So number of satisfying assignments of phi is 1 because x1, x2, x3 all have to be 1, but the number of satisfying assignments of phi prime is 0. So the number of satisfying assignments of for phi plus the number of satisfying assignments for phi prime, this is strictly less than 2 cube equals 8. And option D says that these two are equal to 2 to the n. So this is incorrect. Oh, there's a typo over here. This should be x complement. So now the next problem is consider an n cross n matrix A that has entries from 0, 1. What is the smallest number of non-zero entries that A can have such that the permanent of A is not equals to 0? The answer to the problem is n, and let's see why. So recall that permanent of A equals to sum over sigma in Sn product I in n A I sigma I. So permanent of A not equals to 0 implies there exists sigma in Sn such that A1 sigma 1 up to A n sigma n, all of these are non-zero. In fact, the converse is also true. So This is a by implication because A is a 0, 1 matrix. So since A is a 0, 1 matrix, if such a permutation exists, then at least one of the terms over here would be 1. And since every entry of A is positive or 0, there isn't going to be any cancellation over here. So if one of the permutations is one of these products is 1, then the permanent would be non-zero. So this is the by implication. So what does this mean? This means that the permanent of A is non-zero if and only if for a permutation sigma, A1 sigma 1 to AN sigma n are non-zero. This means that at least n entries of A must be non-zero. Now, this tells us that at least n entries must be non-zero. Now, let's see an example where n entries actually work. Now, let A be the n cross n identity matrix. The permanent of A is equal to 1. Why? Because it's an identity matrix. There's only one permutation for which this is non-zero, and it's the identity permutation. Because A1 sigma 1 AN sigma n not equals to 0, and it's an only if sigma I is equal to I for all I in it. So the permutation of this matrix with just n entries is 1. Now, so not only are n entries required, but n entries are also sufficient for at least one matrix. So the answer is n. The next problem is somewhat complementary. So it asks, consider an n cross n matrix A that has entries from 0, 1. What is the largest number of non-zero entries that A can have such that permanent of A is 0? So the previous question asked us what is the smallest number of uh, non-zero entries that the permanent is non-zero? This is the complementary question. What is the largest number of non-zero entries such that the permanent is 0? And the answer to this is n square minus n. Let's see why. So the proof of this is slightly longer, but we'll do it slow. So now consider the matrix A is equal to so consider the matrix whose consider the n cross n matrix whose first n minus 1 rows are all ones and the last row is 0. Then the permanent of this matrix is 0. That also directly follows from the definition of the permanent. So we can have n square minus n entries. So this tells us that even if we have n square minus n entries, the matrix can have a 0 permanent. So this tells us that n square minus n is a lower bound on this answer. Now let's show that it is also an upper bound. That is, if you have more than n square minus n entries, then the permanent has to be non-zero. So we'll prove the following claim. The permanent of A is not equals to 0. So we want to prove that if A has more than n square minus one non-zero entries, then the permanent is non-zero. That is the same as arguing that if A has at most n minus 1 many zero entries, then the permanent is non-zero. So if we prove this claim, then we would have shown that the answer to this problem is n square minus n. So let's prove this. The proof is by induction. On n, third dimension of A. The base case is n equals 1. Then A has at most 1 minus 1 is equal to 0 zeros. So A is this matrix. Hence, the permutation the permanent of A is 1, which is non-zero. So in the base case of n equals to 1, this claim is certainly true. Now let's look at the induction step. So suppose that true for all n minus 1 cross n minus 1 matrices with 0, 1 entries. Okay, now what we'll do is the following. We'll show that there exists a permutation such that A1 sigma 1 up to AN sigma n is non-zero. And this would prove the claim. So why would this prove the claim? Because we saw in the previous problem that the permanent of an n cross n matrix with 0, 1 entries is non-zero if and only if there exists such a permutation sigma. So we'll show this to prove the claim. Now, because A has at most n minus 1 zeros, no row, or for that matter column, of A can be completely zero. That is, every row or column of A has at least one non-zero entry. In this case, that entry would be 1. Okay, so let I1 be the index of the row with the most number of zeros. Because AI1, because the row AI1 is not a zero row, so not completely zero as we saw before. There exists a J1 in N such that A I1 comma J1, that is the I1 J1th entry of A is 1. So now what we'll do is we'll start constructing sigma. So let sigma I1 equals to J1. Okay. And also let B be the matrix obtained from A by removing the I1th row and the J1th column of A. So basically, we are removing the row and column containing this entry. Okay. Now, if the permanent of B is not equals to 0, then there exists a permanent of P is not equals to 0 if and only if there exists a permutation sigma oh no, there exists, let me write it like this. There exists a bijection F. No, let me call this sigma prime. There exists a bijection sigma prime from n minus I1 to n minus J1 such that uh, AI comma sigma prime I is not equals to 0 for all I in uh, n minus I1. Why? Because as we saw before, since B is in a 0, 1 matrix, its permanent is non-zero if and only if such a permutation exists. In this case, it's a bijection because we are obtaining by removing some rows and columns of it. Okay, so this is true. Now, if this were true, so if we define sigma I is equal to sigma prime I for all I in n minus I1, then sigma is a valid permutation on n. Why? Because clearly sigma is a function from n to n. It's also a bijection or a permutation because sigma prime is a bijection, and in the range of sigma prime you won't find J1, which is sigma I1. So sigma is the valid permutation. So what we have shown, okay, let me write it. Also, AI sigma I is not equals to 0 for all I in A. Why? Because A1 sigma A sigma I1 was J1. So AI1 J1 was or AI1 J1 or AI1 sigma I1 was clearly non-zero. And for the rest of I, it follows that AI comma sigma is not equal to 0 from the way we have considered sigma prime from B. So this is true. So if we can show that the permanent of B is non-zero, then we would have such a permutation sigma. Then as we saw before, this implies that the permanent of A is non-zero. So now let's show that the permanent of B is non-zero. That's the second claim. Permanent B is 0. Okay, so recall that AI1 was the rows with the most number of zeros. Let's consider case 1. AI1 had no zero. So in this case, A and therefore B are all one matrices. Why? Because if AI1 has no zero and it has the most zeros, then other rows of A must also have no zeros. And therefore B must, all rows of B must have no zeros. So A and B are all one matrices. But we know that the permanents of all one matrices are non-zero. So permanent of B is non-zero. In fact, in this case, we directly get that the permanent of A is non-zero as well. But regardless, we only need that permanent of P is non-zero over here. So that's one case settled. Now, case 2 is this. AI1 has at least one zero. Now, we obtained B by removing the AI1th row. So sorry, by removing I1, that is the I1th row from A. So in doing so, we would have also have removed all the zeros that occur in this uh, row, right? Now, since A has at most n minus 1 zeros, B can have at most n minus 1 minus 1 equals to n minus 2 zeros. Since B is an n minus 1 cross n minus 1 matrix with at most n minus 2 zeros, it follows from the induction hypothesis so recall that we assume that claim 1 is true for all matrices of size n minus 1 cross n minus 1, that the permanent of P is non-zero. And this is exactly what we want to prove over here. So this completes the proof. So the answer is n square minus n. Now let's look at the ninth problem. Consider the graph given in the figure below. I'll draw the graph. All the unmarked edges of the graph have weight 1. Then what is the sum of the weighted cycle coverage of this graph? Yeah, so the graph is this. It has 3 vertices, labeled Z, X, and Y. This edge has weight 2. This edge is unlabeled, so it has weight 1. This edge is also unlabeled, so it has weight 1. This edge is also unlabeled, so it also has weight 1. This edge has weight 2. So there's just two edges with weight 2. And we are supposed to find the number of cycle covers. So we are supposed to find the sum of the weighted cycle covers of this graph. Now, recall that set of disjoint cycles such that every vertex is present in at least in exactly, because they are disjoint, at least in exactly are the same. So let's first of, and also recall that the weight of a cycle cover is just equal to the product of the weight of the cycles in it, and the weight of a cycle is equal to the product of the weight of the edges in it. Okay, so now let's list all the cycle covers in this graph. Now, suppose that a cycle cover has this edge from Z to, so suppose that a cycle cover has this edge, this, the edge from Z to X. Then can it have this edge from X to Z? Well, no. Why? Because if we go from Z to X and X to Z, we can't get to Y without taking this edge and then coming back. So in this case, the cycles are not disjoint because both cycles contain Z. So if the cycle cover has this edge, then it cannot have this edge. So okay, let's say the cycle cover has this edge. And what next edge can it have? It can have this edge. And once it has this edge, it is forced to have this edge to go back to Z. So this Z to X, X to Y, and Y to Z is the valid cycle cover. So here's one cycle cover. Let me draw this. Now let's see if this can have any other cycle cover. Now, okay, first of all, notice that this edge must be present in every cycle cover. Why? Because this is the only way to get to X. So if this edge is not there, then X cannot be in the cycle cover. And as we saw, if this edge is there, then we are forced to pick this edge and therefore to pick this edge. So this is the only cycle cover in the graph. Now what's the weight of this cycle cover? It's 2 times 2. 2 times 1 times 2 equals to 4. And since this is the only cycle cover in the graph, the answer is 4. Now let's look at the next problem. So the next problem also asks us to consider this graph. Consider the graph from the previous problem. Suppose that we add self loops of weight 2 to all vertices in the graph. Then what is the sum of the weighted cycle covers of the new graph? So first of all, let me draw the graph. So the graph looks like Z, X, Y. You have, yeah, the answer is over here. So let me draw it. So the graph is this, X, Y, Z. Oh no. Okay, so the answer to this problem is 20. Let me draw the graph in the next. So here's the graph. Z, X, Y. This edge has weight 2, this edge has no weight. So weight 1, this edge has weight 1 because it's not marked. This edge has weight 1 because it's not marked. And this this edge has weight 2. But now we also add self loops with weight 2. So this is our graph. Now let's look at the cycle covers. First of all, the cycle cover from the previous question is still a cycle cover. So this is one valid cycle cover. No, not this edge. This is a valid cycle cover. Now let's see if there are other cycle covers. Now suppose we take this edge from Z to X. Then now we can also take this edge back from X to Z because to include Y we can just use this self loop. So this is also a valid cycle cover. So the weight of this was 4. And now what's the weight of this? It's 2 times 1 times 2 equals 4. That's one cycle cover. Now let's see some other cycle covers also exist. Now, so this was the previous question that we were any cycle cover must have this edge. But now there that constraint is no longer there because we can cover X using this self loop. So let's drop these two edges. Now, oh, I made a mistake in drawing the graph. This edge goes from Z to Y and it has no label, so wait 1. Okay. So what we can do is we can pick this edge, and this edge. So that's also valid cycle cover. I just can't seem to be able to draw this edge properly. And let me draw it like this. Yeah, good. So what's the weight of this cycle cover? It's also 2 times. So it's 1 times 2 times 2. 1, 2, and 2. Then this is also a valid cycle cover. So we can only use just 3 loops. And the weight of this is 2 times 2 times 2 equals 8. So you can convince yourself that these are the only cycle covers. So the sum of the weights is 4 plus 4 plus 4 plus 8 is 20. And that was the answer. So now let's look at the next problem. So given Boolean formulas phi and psi with R and S satisfying assignments, respectively, which of the following can we not construct by combining phi and psi with some other variables and logical operators? So the options are a Boolean formula that has R times S square plus R cube satisfying assignments, a Boolean formula that has R cube plus S, R cube times S plus S square satisfying assignments, a Boolean formula that has R cube times S minus S square satisfying assignments, and a Boolean formula that has R cube S plus 225 S square satisfying assignments. So the answer to this problem is option, option C, and let's see why. So we saw in the class that if we are given two formulas, phi 1 and phi 2. Okay, let me also tell you how many variables there are in. So two formulas, phi 1 in x1 to xn and phi 2 in x1 to xm, suppose n greater than, or sorry, suppose n greater than equals to n, then we can construct let me call this the sum construction for this formula. Phi 1 plus phi 2. And this is in the variables x0 to xn. Here x0 is a fresh variable, and this formula looks like this. X0 equals to 1 and phi 1 in variables x1 to xn, or x0 equals to 1 and x, sorry, x1 must be 0 now. X0 is 0 here, it was 1 and here it's 0. X uh, m plus 1 equals 0 and x n equals 0 and phi 2 in x1 to xn. And this product construction, phi 1, phi 2, x1 to xn and y1 to ym. So here y1 to ym are variables different from x1 to xn, and this is just phi 1 in x1 to xn and phi 2 in y1 to ym. And what we saw was this. Number of satisfying assignments of phi 1 plus phi 2 is equal to number of satisfying assignments of phi 1 plus the number of satisfying assignments for phi 2, and the number of satisfying assignments for phi 1, phi 2 is equal to the number of satisfying assignments of phi 1 and times the number of satisfying assignments of phi 2. So this is what we saw in the class. Now let's look at the options. So Let me show you why options A, B, and B are correct. Using just one of these, option B. The arguments for option A and D are similar. So we want to construct a Boolean formula with r cube s plus s square satisfying assignments. One way to do it is the following. Take phi, apply the product construction on it once to get a formula with r times r equals r square satisfying assignments. Take that formula and phi, again apply product construction to get a formula with r cube equals r square times l, r satisfying assignments. So now we have a formula with r cube satisfying assignments. Take that formula and apply the product construction again to obtain a formula with r cube times s satisfying assignments. Then apply product construction using psi to obtain a formula with s times s equals s square satisfying assignments. So now we have a formula with these many satisfying assignments and this many satisfying assignments. You want to obtain a formula with these many satisfying assignments. For that, you can just apply one sum construction. So you can construct this. Similarly, you can construct these two formulas. Over here, the observation is 25 s square is just s square plus s square plus s square 25 times. So you can apply the sum construction multiple times instead of just one time over here. However, we cannot construct or we do not know how to construct Boolean formulas where the number of satisfying assignment is subtracted. So C is the answer. Now let's move on to the next problem. Which of the following captures the statement of Toda's theorem most accurately? The options are: any language in PH can be decided by a randomized polynomial time Turing machine with access to a parity P oracle. Any language in PH can be decided by a deterministic polynomial time Turing machine with access to a parity P oracle. Any language in PH can be decided by a randomized polynomial time Turing machine with access to a sharp P oracle. And any language in PH can be decided by a deterministic polynomial time Turing machine with access to a sharp P oracle. The answer is D, because recall that Toda's theorem tells us that pH is contained in Fp to the sharp P. So this is what Toda's theorem tells us. Now let's move on to the next problem. So uh, let parity x phi x denote the parity of the number of satisfying assignments x of phi. That is, parity x phi x is true if phi x has an odd number of satisfying assignments and false if it has an even number of satisfying assignments. Given Boolean formulas phi x and psi x, which of the following is or are true? Select all that apply. Option A. There is a Boolean formula gamma such that parity z gamma z equals parity x phi x or parity y phi psi y. There is a Boolean formula gamma such that parity z uh, gamma z equals to parity x phi x and parity y phi y. There is a Boolean formula gamma so that parity z phi gamma z equals to not parity x phi x, and there is a Boolean formula gamma so that parity z gamma z equals to parity x phi x x or parity y phi y. So the answer to this problem is all of these. Let's see why. So we've also seen this in class that given Boolean formulas, so for option B, so let's first work with option B, this and option. Uh, let gamma z, to wait, let parity z gamma z be this formula. parity x, y, phi, psi. Now, we saw in problem 13 that this the number of satisfying assignments of phi dot psi is the number of satisfying assignments of phi and psi, because the number of satisfying assignments of phi dot psi is odd if and only if uh, phi and the number of satisfying assignments of phi and the number of satisfying assignments are both odd. uh, Parity z gamma z, oh, z gamma z is the required formula. This proves that P is correct. Now let's look at option C. Parity z uh, gamma z P. Here U is some extra variables. So what does phi plus 1 mean? It's a Boolean formula whose such that the number of satisfying assignments of that formula is exactly equal to the number of satisfying assignments of phi plus 1. And you can easily construct such a formula using the sum construction that is found in problem 11. So now, a number of satisfying assignments of phi plus 1 is equal to the number of satisfying assignments of phi plus 1. So, the number of satisfying assignments of phi plus 1 is odd if and only if the number of satisfying assignments of phi is even. Hence, parity z gamma z is the required formula. Required formula. Okay, now let's look at option A. So in option A, we want to construct a formula with an or over here. Now, what do we know? For any variables u and w, okay, sorry. Okay, so for any Boolean variables a and b, a or b is just this from De Morgan's law. Okay, so what we can do is using these two constructions and this identity, this works. So first we want to take not of A. So in our case, A and B would be this form, these two formulas. Parity x phi x and parity y phi y. Parity y psi y. So this formula, I forgot the parity outside. X, y, and Q are the extra variables that you might need in the sum and product constructions. So first we want to take the negation of parity x phi x, which as we saw over here is just this formula. Parity of phi plus 1. Then we want to multiply this with the multiply because of this reason, multiply this with the negation of parity y psi y. But as we saw over here, parity y psi y is this. And now we want to take the negation of this all, so we just multiply by 1. So this formula works. Now, okay, let's observe what we did over here. Over here, we used this identity and the constructions that we had for or and not, and not to construct a formula for or, right? Now, any Boolean function can be expressed as combination of or and nots. So basically using exactly the trick that we used over here, for we can construct a formula for XOR by doing the following. Writing down XOR in the form of ands and nots, and then basically using that expression and the constructions. Constructions for and not. So using these, we can also construct a Boolean formula gamma, so that parity z gamma z equals to parity x phi x or parity y psi y. So that's all the problems for today.